In this video, I want to talk about operations on matrices. Operations are things like addition and subtraction. So we have binary operations. Binary means we do it to two matrices of addition, subtraction, and multiplication. Then we have unary operations. Unary means we do it to just one matrix of scalar multiplication, transposition, and derivation and integration. These make sense if the entries of the matrix are functions. Now this topic of derivation integration has got a lot of calculus in it. So I think in one video I'm just going to talk about the other operations, and then I'll make a second video about the calculus part. So let me get rid of this for now. And let's start with addition and subtraction. So we define A plus B to be the matrix whose ij entry is the ij entry of A plus the ij entry of B, the easiest possible thing. So for example, we have 1, 3, negative 1, 4 plus 0, 2, 3, negative 1. That equals 1 plus 0 is 1, 3 plus 2 is 5, negative 1 plus 3 is 2, 4 plus negative 1 is 3. So the easiest possible thing that addition of matrices could be. Now I should mention this only makes sense if the matrices are the same size. We can't add a 2 by 3 matrix with a 3 by 4 matrix or something like that. Now subtraction is exactly what you would think it would be also. So if we write A minus B, that's the matrix whose ij entry is ij entry of A minus ij entry of B. Again, the matrices have to be the same size. We just subtract corresponding entries. 1 minus 0 is 1. 3 minus 2 is 1. Negative 1 minus 3 is negative 4. 4 minus negative 1 is 4 plus 1, which is 5. And maybe it's worth mentioning that if we take a matrix and subtract itself from it, like 1, 3, negative 1, 4, minus 1, 3, negative 1, 4, we get 1 minus 1 is 0, 3 minus 3 is 0, negative 1 minus negative 1 is negative 1 plus 1 is 0, 4 minus 4 is 0. So we get a matrix called the zero matrix. Sometimes we just write that as a big 0. So I wrote that as a big 0. Now, so that's easy. I don't want to explain anymore. Let's look at matrix multiplication, which we've done before, but I want to look at it a little more closely. In particular, I want to write a formula for the ij entry of the product matrix. So if A times B equals C, then Cij is what? Now remember, AB is only defined if the second dimension of A is equal to the first dimension of B. So let's say A is an m by n matrix. B would have to be n by something. Let's say n by p. And then C would be an m by p matrix. So what is Cij? I think it would be best if I erase the whole board and then use everything to show this. If AB equals C, then the ij entry of C is what? A is an m by n matrix, B is an n by p matrix, and C has to be an m by p matrix. Well, when I multiply matrices, I like to drop the A lower than the B. So let me start writing B entries here. So we've got B11, B12. If B is an n by p matrix, that means there's p columns, so the last entry in the first column would be B1p. Then below that we have B21, B22, up to B2p. And if B is an n by p matrix, then we have n rows, and the nth row is Bn1, Bn2, up to Bnp. And then the entries of A are A11, A12. If A is an m by n matrix, then there are n entries in the first row, so A1n is the last one. Then in the second row we've got A21, A22, A2n, and it's an m by n matrix, so the last row is AM1, AM2, up to AMN. This is a little crooked and it's bothering me. Let me rewrite the last row of B here. Bn1, Bn2, Bnp. There now. How do we get the ij entry of this product matrix, which we'll write right here? Well, every entry in the product matrix comes from looking at one row of A and one column of B. The ij entry is going to come from looking at the ith row of A and the jth column of P. Remember, we go multiply, 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 etc., and add the products together. So Cij is going to be AI1 B one J, because we're looking at the jth column in the ith row, and then A in the ith row we have AI2, and then in the jth column we'll have B2J, and then the third entry of the ith row of A will have AI3, and then in the third entry of the jth column of B we'll have B3J. So what we get is a sum. I'm going to have to lift this up slightly. As k goes from 1 to n, a I k b k j. So there we go. A I k b k j in the sum. Well, another way to think of this is, so we've got a row vector here, the ith one, and a column vector here, the jth one. If you remember from calculus what the dot product is, what we've just done is take the dot product of the ith row of A and the jth column of B. So we could either write this as a sum, as k goes from 1 to n, a I k b k j, or we could write it as the dot product of the ith row of A with the jth column of B. All right, those are the binary operations. Now let's look at a unary operation. One is scalar multiplication. Let me use r as my scalar because I just used k in my sum here. Let's look at r times a. So r is basically a number and a is a matrix. And the ij entry of this scalar product of r and a is just r times the ij entry of a. So if we have, for example, negative 3 times the matrix 1, 3, negative 1, 4, we just multiply all the entries of the matrix by negative 3 and get negative 3, negative 9, 3, negative 12. And I guess we could look at scalar functions of a variable if the entries of the matrix are also functions of a variable. So for example, we could have t times, let's say we have e to the t 1 plus t sine t and 2t squared. We would just multiply all these functions in the matrix entries by t, and we would get t e to the t, t plus t squared, t sine of t, and 2t cubed. So scalar multiplication is very easy. Just multiply everything in the matrix by that scalar on the outside. All right, I want to point out some properties of these operations. So if we multiply 3 matrices, assuming that the dimensions of these matrices line up correctly so that we can do the multiplication. That is, the second dimension of A and the first dimension of B have to be the same. The second dimension of B and the first dimension of C have to be the same. If that's the case, then if we multiply B and C first and then A later, or A and B first and C later, we get the same thing. So because of that, we can just write A, B, C. It doesn't matter whether you think of it as multiplying A and B first or multiplying B and C first, because you get the same answer anyway. That's called associativity, if you want to give it a fancy name. Now if A, B, and C were numbers, you know that A times B plus C would be equal to AB plus AC. And in fact it is with matrices too. Assuming that, well, B and C have to be the same size matrix to be added together, and then the second dimension of A has to be equal to the first dimensions of B and C, so that we can do that multiplication there. Similarly, if A and B have the same dimensions, and the second dimensions of these are equal to the first dimension of C, then we can write A plus B times C and distribute the same way. That equals AC plus BC. So as far as these properties go, the matrices work just like numbers, because this is exactly what we would expect based on what we know about numbers. Recall, we let I be the matrix that has ones on the diagonal and zeros every place else. The identity matrix acts a little bit like the number 1, in the sense that when we multiply by it, nothing happens. So we can multiply it by it on the left, multiply by it on the right, and we just get our matrix back. Now we write capital I for the identity matrix of size 1 by 1, 2 by 2, 3 by 3, 4 by 4, which maybe is an abusive notation because we're using the same letter every time. So for this to be defined, let's say A is m by n. I really want this identity matrix to be the m by m identity matrix. And I want this identity matrix to be the n by n identity matrix. Let me do an example so you can visualize this a little bit better. Let's let A be the 2 by 3 matrix 1, 3, 2, negative 1, 4, 5. So by IA, I mean the 2 by 2 identity matrix. I times A. I'll just leave it here. So 1 minus 0 is 1. No, I'm going to write the, I'm going to move this A over so we can see it better. So this way when I multiply my product will go right here. So I've got 1 plus 0 is 1, 3 plus 0 is 3, 2 plus 0 is 2, 0 minus 1 is minus 1, 0 plus 4 is 4, 0 plus 5 is 5. So we just got the same matrix back. And if I want to multiply that on the right by the identity, then I'm talking about the 3 by 3 identity matrix. My product answer is going to go right here. So I'll have 1 plus 0 is 1. 0 plus 3 plus 0 is 3. 0 plus 0 plus 2 is 2. Negative 1 plus 0 is negative 1. 0 plus 4 plus 0 is 4. 0 plus 0 plus 5 is 5. So again, we get the same matrix back. So if we think of I, the identity matrix, kind of like 1 when we're multiplying, then again we've got a rule that works just like the numbers work. But I have a small warning for you. A, B, and BA don't have to be the same. In fact, usually they're different. We could think of some matrices A and B where we get the same answer multiplying A by B and B by A, but usually these are different. So this rule works different from numbers because, well, 2 times 6 is 6 times 2. So we're used to reversing the order of multiplication of numbers, but we can't do that with matrices. Sometimes BA is not even defined because the dimensions don't work out. But even if BA is defined and AB is defined also, AB and BA don't have to be the same, and usually they're not. Well, the properties of scalar multiplication are pretty much exactly what you would expect. Oh, I didn't define scalar multiplication. Did I? Oh, yes, I did. Okay, the properties of scalar multiplication are just what you would expect. So let's say R1 and R2 are scalars, and we have matrices A and B that are the same size. And if we multiply R1 by A plus B, then we can distribute just like we can with numbers, and that's R1A plus R1B. If we have R1 plus R2, so a sum of scalars times a matrix A, that turns out to be R1A plus R2A, so we can distribute there too. And then if we have R1, R2A, so scalar times the matrix, well, we know that scalars can multiply in either way. So that's R2, R1A. And actually we can put parentheses in there however we want. We could say that's R1, R2, in parentheses A, or R1 times R2A in parentheses, or R2 times R1A in parentheses. So it works exactly the way we think it should. All right, now let me bring up the unary operation of transposition. Sometimes it's useful to switch the rows and columns of a matrix. And we define A transpose to be the matrix whose ij entry is the ji entry of A. So we take the row index and the column index and we switch them. So for example, if A is the 2 by 3 matrix 1, 3, 2, negative 1, 4, 5, then A transpose is the 3 by 2 matrix 1, negative 1, 3, 4, 2, 5. So we just sort of flip it along the diagonal. I guess you could draw a line there and reflect the matrix in that diagonal line. Now if we transpose the matrix twice, we just get the same matrix again. Obviously if you reflect twice in that line, you just get the matrix back. Or if you switch rows and columns and then switch rows and columns again, then it's like you didn't do anything. If we take a sum of matrices and transpose them, then we just get the sum of the transposes. If we take a scalar product of a scalar and a matrix and transpose that, that's the same thing as transposing the matrix first and then doing the scalar multiplication afterward. This means that transposition is a linear function. Remember, we talked about linear functions in the first lesson. So that means that if we take R1A plus R2B and transpose it, so by this rule we can transpose the two pieces individually, and by this rule we can pull the constant out. So that's R1A transpose plus R2B transpose. So that means that transposition is a linear function, just like the derivative. Alright, and I realize these videos just loop around to the front when you're finished, so maybe to stop a video I'll like put the curtain up here and then stop it